Hello and welcome. I'm Ruoxi Shi. I'm glad to present RendNet Unified 2D 3D Recognizer with Latent Space Rendering, a new design for visual recognition tasks on vector graphics. Vector graphics, or VG in short, is an emerging format for visuals. From logos to floor plan designs, VG has been ubiquitous in our daily life. It has infinite resolution and has higher level structural information in contrast with raster graphics or RG. However, since human designers craft VG by looking at the rendering result, or RG, there may be small, unperceivable topological errors like this base top symbol in a floor plan. The line and the curve should be connected at this point, but is off by a very small gap. These add noise to VG data that can be filtered by rendering to RG. Also, we have large-scale pre-trained models available for RG, since it is the format for natural sensors like cameras and lidars. So it is best to combine both formats to get the best of both worlds. But how? Recent work on multimodality learning shows that directly fusing results of VG and RG models is likely to fail to exploit relations between VG-RG and thus does not work well. This is also confirmed later by our experiments. So our solution is rendering. The renderer knows the correlation between sparse VG attributes and the rendered RG pixels. To utilize this for learning, we choose to represent the VG as a hypergraph, and we designed a rendering method taking node embeddings as input attributes and yielding RG, but replacing the output color space in ordinary rendering by the model latent space. The rendering method we designed is termed latent space rasterization, or LSR in short. It implements a renderer in latent space via rasterization. Rasterization is a mature technique in computer graphics. Similar to that technique, our LSR has two major steps: fragment generation and vary interpolation. Due to the multiple shifts between parameter space for VG primitives and Euclidean space, the LSR has 4 steps in total. Fragment generation, generating a dense point cloud from VG primitives. Triangulation, assigning each point to a triangle in the parameter space. Interpolation, linearly interpolates the attributes from node embeddings on simplex vertices into each fragment or point. And finally, we remap the representation from parameter space to Euclidean space. And by relating VG and RG with LSR, we can now build our pipeline. We represent VG as a hypergraph. Nodes are vertices. Edges represent curves. Hyperedges represent surfaces that connect multiple vertices. The RendNet is made of multiple residual blocks as well as a final global aggregation block. In the vector stream, upper ones in figure, we use hypergraph neural networks to aggregate node embeddings mainly based on connectivity induced from VG. In the raster stream, we apply LSR to form a point cloud representation and apply local point nets centering on each node to aggregate batch information from RG to the nodes. We evaluated RendNet on 2D detection and classification, as well as 3D classification and similarity estimation tasks. For 2D, we run RendNet on SESIT floor plan dataset. Our method outperforms the previous state-of-the-art Latent that utilizes the VG only, as well as various famous RG detectors. For 3D, we evaluated RendNet on FeatureNet and Cluster 3D datasets. Our method also achieves state-of-the-art precision, while keeping fast compared to SOTA point cloud methods like DGCN and PointNet++. The ablation study shows that each component is helpful in our method. Also, the error is significantly lower compared to a simple ensemble of VG and RG models. The representation visualization shows that RendNet captures more refined structures than PointNet. Thank you.